Welcome to the first lecture of Unit 2, Sculpturing the Earth's Surface for ESC1000, Introduction to Earth Science. This lecture will cover material in Chapter 4 of your textbook and will deal with weathering, soil, and mass wasting, three important processes that shape the Earth's surface. Now, before we begin, Unit 2 is concerned with the shape of the Earth's surface, and that is, in general, considered by geologists to be what's called geomorphology, or the study of the Earth's surface. Geo and morphology. Geo meaning Earth, morphology meaning shape. In Unit 2, we'll be dealing with weathering, soil, and mass wasting in Chapter 4, important processes that control over long and short periods of time what the Earth's surface looks like. We'll be looking at running water and groundwater in Chapter 5, and glaciers, deserts, and wind in Chapter 6. All are processes that make the Earth look like what it looks like today, and have been operating throughout geologic time. The Earth's processes in this chapter that we'll be covering are weathering, mass wasting, and erosion. Weathering is essentially the disintegration and decomposition of material, or the breaking of material, geologic material at or near the Earth's surface. That can happen through physical means, mechanical means, or chemical means. Oftentimes, it's a combination of both. In fact, dominantly, or most often, it is a combination of chemical and physical processes that produce weathered material. Mass wasting is slightly different than weathering. Weathering is really just the fragmentation or the destruction of material, or changing of the physical form of that material into smaller pieces. Mass wasting is actually movement of geologic material under the influence of gravity. So that's going to happen downslope in most cases. Erosion is slightly different than mass wasting in that erosion is the incorporation and transportation of geologic material by another agent, usually water, wind, or ice. So it's not due to gravity, it's due to something else is transporting that material that has been weathered. So weathering, mass wasting, and erosion all go together, but weathering has to happen before mass wasting or erosion can occur. When a rock is maintained in its primary physical state, that is, if it remains as an intact unit of material, it's not going to be able to move due to gravity, so mass wasting won't occur, and it won't be able to be moved by agents of transportation, water, wind, or ice. So only when weathering occurs can mass wasting and erosion then subsequently follow. There are two kinds of weathering that geologists talk about, although I caution you about thinking of them in distinct kind of binary or separate terms. Mechanical weathering and chemical weathering are the two modes of weathering. However, they often happen in conjunction or simultaneously. Sometimes one type, mechanical or chemical, is the dominant force, but it's hard for one to act in complete isolation from another. So, mechanical weathering is basically the breaking of rocks into smaller pieces, just what it says. Different processes can cause mechanical weathering. Frost wedging, tectonic unloading, biological activity are three of those processes. This is an example of frost wedging. And frost wedging is based on, or is caused by an interesting property of water. Water is a pretty amazing molecule, and we'll be encountering water throughout this entire course. But one of the interesting properties of water is that it's most dense. Most materials get denser as they get colder. Water is actually interesting. Water at normal Earth temperatures, that is, 100 degrees F or 120 degrees Fahrenheit down to below freezing, temperatures that we're used to as human beings, water is typically liquid. Oftentimes it's gas, water vapor. There's lots of water vapor up in the atmosphere and water vapor all around us. It can also take the shape of ice. It can be solid water. What's interesting about water, differently than most materials, is that most materials, when they get colder, they become denser and they take up less space. However, the water molecule is really, really fascinating in that its densest point is 4 degrees C. That is, it's still liquid when it's densest. So water at 4 degrees C takes up a smaller amount of space than it would if it were at 20 degrees C or 30 degrees C, pretty warm. or 100 or 90 degrees C, very warm, almost hot, but it also takes up less space than it would at 2 degrees C or 0 degrees Celsius or minus 10 degrees Celsius. And when water is frozen, it's actually less dense than it is when it's liquid. So liquid water, if it gets into a crack in rocks, either a small crack in a small rock or a large crack in a large rock, such as a mountain, that water gets into a space, and as it gets colder, it gets denser and takes up less space, and more water can percolate into that crack. But eventually, when it starts to freeze, it actually expands. It takes up more space. And as that expands, it has enough mechanical force, enough power to actually crack rocks and break them off. That's what's called frost wedging. This diagram up here shows the essential nature or the essential process by which frost wedging occurs. Water that was liquid is in this crack of rock. As it freezes, it expands and causes this chunk of rock to push up and out, this block of rocks over here to push outward. And eventually, over geologic timescales, you can produce enough of that frost wedging material downslope of mountains that you can create these large talus slopes. This is the label of the talus slope over here. So this is an example of frost wedging and what we'll get to in a minute, which is called mass wasting. Unloading or tectonic unloading or exfoliation of igneous rocks, or any kind of rock for that matter, can occur. It's another kind of mechanical weathering. It can occur due to or over long periods of geologic time. Large bodies of igneous rock can form deeper within the earth due to intrusions of magmatic material and cooling, and you can get deep crustal or underground bodies of rock. This is an example of a pluton that has lots of earth, soil and other kinds of rock material over it, and this is the land surface up here. Over geologic time, as that Earth's surface erodes or somehow weathers and disappears, which it can do due to water or due to lots of different things, you can expose that large igneous body. Well, in this situation, all of the earth over top of the large igneous body created a lot of pressure and kind of kept the rock intact. Well, when that's exposed and there's no longer this force above it, that rock can actually expand due to the kind of or to accommodate kind of crustal or crystallographic aspects. So it basically starts to separate and cracks will form, joints. If you really zoom in here, joints can form, which can be then weathered in different ways. For example, frost wedging could come into play into those joints. Biological weathering, which is mentioned, is kind of a less common example of mechanical weathering, but you can get biological agents that will act on rocks, will disrupt or disturb or burrow down through and cause mechanical disaggregation and weathering. The second main type of weathering is called chemical weathering. Chemical weathering is exactly what it says. It's a chemical process. So instead of physical breakage of rocks, chemical weathering is based on chemical reactions, most typically involving oxygen with oxidation or carbon dioxide. CO2 is commonly dissolved in water. There's always some CO2 in natural waters or surface waters on the surface of the earth. And when you have dissolved CO2 in water, actually that water becomes slightly acidic. It's just like carbonation in a soda or other beverage that's carbonated. Dissolved CO2 actually makes that solution slightly acidic, and when water is slightly acidic, it has the ability to be more chemically reactive with material that it comes in contact with. So in chemical weathering, water is critically important. Rates of weathering are what geologists are very, very interested in because they can vary over long periods of geologic time, and they have a lot of influence on atmospheric chemistry, ocean chemistry. They're influenced by tectonics, that is mountain building. They're influenced by subduction, that is plates subducting down and back down into the mantle. So weathering rates can often be influenced by very, very large and slow geologic processes, which makes them quite interesting. mechanical weathering and chemical weathering work in conjunction, especially considering that mechanical weathering increases something called surface area. That is how much of a surface of a rock is exposed to weathering forces. Different rocks weather differently. Minerals that make up rocks can vary in composition and reactivity or solubility. And they also, as we learned back in the earlier chapters, the way rocks and minerals cleave and split apart can influence how jointed or how many cracks and fractures appear in a rock body. And the more cracks and fractures that appear or that exist in a rock body, the more surface area there is, or the more surface space there is for weathering reactions to occur. This is a brief example of what we're talking about when we talk about surface area. These three pictures of rock represent the same amount of rock. If you were to weigh this rock in this example and weigh these 8 pieces of rock and weigh these 96 pieces of rock, they would all weigh exactly the same. So it's the same amount of rock in terms of mass or weight, what we often think of as weight. Exact same amount of rock. But as the example shows, the amount of surface area, the amount of rock that is exposed to chemical or physical or weathering agents, that is the amount of rock surface that we can see with our eyes, is much different. In this example, where the rock is just one entire piece, you have a unit length of 2 units on one side, the other side, and vertically, so it's a cube. So you have 24 square units of area in this rock. But this rock, this section over here that weighs exactly the same, just because it's split up into 8 pieces, has double the amount of surface area available for weathering reactions. So which one of these do you think the weathering would occur faster? On this one, where there's 24 units, or if there's much more surface area, do you think the weathering would occur in this rock much faster or slower? Sliding over to this example, here we have these 8 chunks that came from this big block. Each of these 8 are split into 8 more pieces. So now we have 96 units of the exact same mass of rock as we had here and as we had here. This rock over here now has 96 square units of surface area, even though it is comprised of the exact same mass or amount of rock. So we're doubling the surface area again. So if we look back from the original, 24 units of rock, quadrupled to this area just by dividing it up into much, much smaller pieces. So this is an example of mechanical weathering. Let's just say chemical weathering, which more surface area means the more weathering agent, water, water would dissolve CO2 or oxygen in it. The more water that comes in contact with more surface area, the faster it's going to weather. So in a chemical weathering perspective, this rock will weather much faster than this, and this will weather still even faster than this. But going from here to here to here is also an example of mechanical weathering, that is the breaking of the rock. So here we can see how chemical and mechanical weathering work hand in hand. That the more a rock is mechanically weathered, the more it gets chemically weathered because of the more surface areas available. Rates of weathering are controlled over long periods of geologic time by climate. That is the long-term averages in the weather. It's not just weather, whether it's rainy one week or rainy or cold over a couple days. Climate is the long-term averages of weather. So temperature and moisture are the most critical factors in chemical weathering, and actually in mechanical weathering too. Typically, when you have warm temperatures and lots of moisture, chemical weathering rates are high. When you have cold temperatures and abundant moisture, you have physical or mechanical weathering. And when you have low moisture, you typically have, no matter if it's hot or cold, you have mostly mechanical weathering. Moisture or water is really, really important for chemical weathering. This is just an example of a field site of jointing that is an influence on mechanical weathering. You can see this rock is particularly significantly fractured and cracked, usually along some sort of structural aspect of the rock. If it's a rock made up of certain types of minerals, maybe those minerals cleave on bedding or on planes that tend to go in non-normal, non-cubic, but in orthogonal directions. If it's a sedimentary rock that is stratified with layers, perhaps those layers are in this direction as I move my light, and it has cleavage directions or fracture planes in this direction. These fractures can also be caused by tectonic forces. That is, as rocks are deformed and bent and folded, they can also crack in certain ways, oftentimes parallel or in some relationship to the direction of force or stress. But this is a rock that has significant mechanical weathering, and probably due to the fact that it has significant mechanical weathering, has a greater likelihood or a higher rate of chemical weathering as well. Just imagine whether this rock would erode or would weather like this if it did not have the joints exhibited in the picture. Moving on to the second aspect of the three that we're talking about in this chapter that shape the Earth's surface, or the second aspect of a geomorphology in this chapter. Soil. Soil can be thought of as an interface. Oftentimes we think of soil as being something you grow crops in. We have a general idea that soil should be, rich and dark and full of organic matter. But in earth science, in the study of earth science, we think of soil less as a specific thing that produces crops that is nutrient rich and that farmers use to grow food, but instead as an interface in the earth system. That is a combination of both geologic materials or mineral matter, water and air. So it's an interface between the geosphere, the hydrosphere, which is water, and the atmosphere, the air, or the gas layer that surrounds the Earth. So soil is an interface or a combination of these three things that supports the growth of plants. But soil doesn't necessarily have to support the growth of plants necessarily. Like I said, we often think of soil as having to do with farming, and that's true, but what we don't often think about is that soil contains a significant portion of water and air, things that are not necessarily physical or at least not necessarily solid. This example or this illustration shows how trying to get my little spotlight. There we go. This pie diagram shows how much of soil is actually composed of mineral matter and organic matter. Only about half of it total. The other half is comprised of water and air, and those can vary depending. Water tends to fill in the spaces between the mineral and organic matter grains, or air does. If it's particularly dry soil, you might have more air than water, and if it's particularly wet soil, you might have more water than air. But nonetheless, this illustrates the point that about half of soil tends to be non-solid. Soil is described and classified just like rocks and minerals are described and classified by scientists, or biological organisms are described and classified using what's called a taxonomy. That is a naming system. Soil is classified. Taxonomic classification system is based on texture and structure. Texture refers to how the particles are organized, or the range of particles, how the particle sizes are distributed in the soil. Sand, silt, and clay are ways of describing grains of particular size. They do not necessarily mean they're limited to exactly what I'm saying. That sand is literally a description of a grain size. Silt and clay are literally descriptions of grain size. If something is sand, it can be sand of any kind of mineral. It doesn't have to be white quartz sand that we see at the beach. There's lots of different sands in the geosphere. Loam is a mixture of all three sizes, all three grain sizes that you see here. And is typically the best for growing crops, for plant life. This is a ternary diagram, it's called, and this is just an illustration of how the different soils are classified. As we said before, loam is the perfect balance between sand, clay, and silt, or most suited for growing crops or plant life. But what this diagram is, it often confuses people. But what it really is a way of showing mixtures of multi-component, or showing multi-component mixtures, or describing multi-component mixtures. But you can view it as kind of mixtures of two things at a time. So in a ternary diagram, we have one what's called end member, that is sand, all the way over here, percent sand. If we go follow this up to 100% sand right at this point, if something were right there, it would be 100% sand. If we follow it down, something that is 0% sand, but look at this scale, percent silt. 100% silt is considered silt. If we follow this scale, we'll just go back over here. We're looking at percent clay here. So we go up from low percent clay all the way up to high percent clay. And up here we're at 100% clay. So if something were, say, 60% clay and 40% silt, it would fall along this line right here. 40% silt, 60% clay. But what if something were 60% clay, 20% silt, so 60% clay, 20% silt, and 20% sand? So we find our 20% sand line, we drive it over, we get to our 60% clay line, and we're on our 20% clay line. Look, we're still in the clay zone in terms of the taxonomic or classification system. If we find, let's say we have an example of, let's go 60% sand, 30% clay. So we have 60 and 30. That means we must have 10% left, right? So we have 60% sand. Find our sand line, which is the green line. We go up to our 30% clay line, which is here. And we should, oh no, I did that wrong. It should be right here. So our 60% sand line goes here, our 30% clay line here, and we happen to be on our 10% silt line right there. So we're right there, we're in the sandy clay loam zone. This is not critically important. You're never going to see on a test, or at least in the midterm or final, apologies. You're not going to see in the midterm or final an example of this soil chart and say, tell me what percentage, 20% sand, or tell me the type of soil for 20% sand, 70% silt, and 10% clay. You won't find that. But this just illustrates how soil scientists classify soil. Controls of soil formation are fairly intuitive. Like soil is formed based on, or the composition of a soil is based on what the parent material was, whether there was soil or bedrock, as well as the composition of any soil that is added to it, that's carried from elsewhere and deposited. Time influences soil formation quite dramatically. The longer regolith or geologic material weathers and is combined with atmosphere and water and organic matter, the more developed the soil can become. Usage also can play a role in soil development. That is, the longer a soil is utilized by organisms, including humans, can influence its composition. Climate and plants and animals also influence the soil's physical and chemical properties. Plants and animals also produce the organic matter. Decaying dead plants and animals add organic matter to the soil, and animals actually don't have to be dead to add organic matter to the soil. Normal biologic processes do that. Soil not only can be classified and named in terms of what types of soil there are, but it can also, classifications also extends to what's called a soil profile, that is looking at soil down into the ground as it varies. So surface soil is oftentimes quite different than soil at depth is, and that's because different processes are taking place. Up in the upper reaches or the upper sections of soil that's very close to the Earth's surface or at the Earth's surface, there's lots of oxygen or lots of air, there's lots of water, and it's relatively young because the materials there are relatively new or newly added. As you go deeper down into the soil zone, you'll find material that is much older. Sometimes organic matter will drop off dramatically as organic degradation processes have had longer periods of time to act. So soil is often described as a soil profile, and a soil profile has different horizons or zones or layers. In temperate regions, you have the top organic matter, then going further down, organic and minerals, and then further down, you have oftentimes little organic matter, and you're mostly left with refractive geologic materials, mineral matter in small size fractions. In temperate regions, again, you oftentimes have areas where soil is accumulating, and then you have zones where it's being altered, typically. Zones O and A are considered topsoil. When you buy a bag of topsoil at Home Depot, it represents soil that's rich in organic matter and mineral matter. O, A, E, and B, that is the zone of organic matter, organic and mineral, and then straight mineral matter, where it's being accumulated, is called solum, or true soil. That's what soil really is. This is an example of, or a graphical representation of a typical idealized soil profile. And remember, we have different kind of zonal areas, where we have the O horizon, remember, which is the zone of very, very organic rich. That's at the very, very top. This is where leaves, plant litter, old plants are decaying and accumulating, very little mineral matter. The A horizon, where you have decayed organic matter mixed with minerals, is below the O horizon. And then the E horizon is where you have very little organic matter. It's mostly mineral matter. Clays are depleted. Soluble stuff is washed out as water percolates down through, and what you're left with is kind of the leftovers, the silicate-rich minerals, the rocky stuff, in a way. Down in the subsoil zone, the B horizon, which is part of true soil or solum, the B horizon, you've got the zone of maximum accumulation of clay. That is, it's often very, very fine. Remember, clay is a very fine grain size. It can be different colors, but often is red due to iron oxidation. In Florida, you would often find very, very whitish zones where there's lots of calcite deposits. There's lots of carbonate minerals in Florida, and so typically as you dig down below the A horizon, you'll find it very, very, very light colored, and that's due to the mineralogy of the region. Typically carbonate rich. And then down into the C horizon, again, you're going to have partially weathered parent material, which is usually mechanically and chemically weathered bedrock, and moving further on down you get to the rock, the mineral component of a soil. Classifying soil, as we've said before, is called soil taxonomy. It emphasizes or is based on physical and chemical properties of the soil profile. This is a map of different types of different generalized regions of soil around the world. As we discussed weathering earlier on, we talked about hot, humid areas as being dominated by chemical weathering. So in the tropics, Central America, southern United States, especially in the temperate East Coast, tropical and subtropical. On the southern South American continent, we're talking about northern South America. The mid latitudes, or the tropical latitudes of Africa, and moving on into Asia, are characterized by soils that are clay rich, chemically rich, and organic matter rich. Further in the north, we have typically where mechanically weathering is dominant and there's less biological productivity, you have soils that are generally or can be very thin. The organic layers can be very, very, very thin just due to accumulation rates are slower of organic material. But those soils can be still quite nutrient rich. The third aspect of this chapter is called mass wasting. Moving on from soils, mass wasting is the this is the second aspect of this chapter. The third aspect will be erosion. The second aspect is mass wasting, and that is downslope movement of rock, or the movement of geologic material due to gravity. Erosion is going to be due to physical transport agents like water, wind, and ice. But what's interesting about, as we get on later on, is that water is often controlled by gravity as well. Movement of water is controlled by gravity in many cases. Anyway, mass wasting is the movement of rock material, soil, regolith, downslope under the direct influence of gravity. That's the agent of transport. Gravity is the sole controlling force. Oftentimes, mass wasting can be triggered by different parameters. That is, if a material, a loosely consolidated, non-lithified material is saturated with water, it can start to behave as a liquid. This is called liquefaction. It can move things rapidly down slope. Other triggering factors, very, very steep slopes. Materials have, or loose, unconsolidated materials have a characteristic called the angle of repose, which is basically the angle at which a pile of this stuff can accumulate. So if you were to take a handful of sugar and basically let it dribble out of your hand into a single pile onto the counter, and look at how conical or how steep the slope of that pile were to be, and then were to take, let's say, a handful of handful of anything, granola, M&Ms, handful of M&Ms, and do the same test, your pile of M&Ms would probably not form a slope or a mountain or a hill with as steep sides as that pile of sugar. And that's because of the way those grains interact with each other, how they kind of grab onto each other and fit in and snug themselves in tightly. Angle of repose is different for different materials and different minerals, and can influence whether a material can accumulate onto a slope or whether it basically gets to the point where it just comes tumbling down that slope in a mass wasting event. Vegetation can oftentimes prevent or influence mass wasting. Vegetation tends to have the ability or characteristic to anchor slopes and to maintain cohesion. Ground vibrations from earthquakes and other industrial processes, and industrial processes such as building, construction, if they're large scale, surveying, mining can cause vibrations that can trigger mass wasting events. Usually they're fairly, well, we often think of them as catastrophic, but there are some very, very slow mass wasting events or mass wasting types. Generally, types of mass wasting are defined by the material as well as the type of movement, whether it's a fall, that is pieces literally falling through the sky from one source to the place where they come to rest, a slide moving along a well-defined surface, or a flow moving as a viscous fluid, which can happen very, very slow or quickly. Mass wasting is also defined by the speed at which it occurs, so fast or slow. So slumps are rapid movement along a curved surface, and they often occur on oversteepened slope, that is, slopes that are beyond or past the angle of repose. There's an example of a slump that when Earth in this unconsolidated material becomes either saturated or somehow a triggering event occurs, this material has decided or has started to move down slope, and it tends to, those planes of weakness tend to tend to move along curved surfaces. Down at the bottom of that slump, you have what's called an earth flow, that is, Earth behaving as a liquid or liquid-like, and slumping or moving somewhat rapidly in a way that is reminiscent of liquid movement. Other forms of rapid mass wasting are rock slides, which is exactly what it sounds like, a movement of bedrock or fragments of bedrock down a steep slope, or debris flow. Debris flow is oftentimes occurs in flooded stream beds where lots of bed load or stream flow is occurring, and lots of solid material is entrained in a channel of water, which it becomes basically more mud, more solid than liquid. And those are often particularly destructive. Other types of debris flows can be volcanic in origin. The name for that is a lahar, and you can have that because oftentimes you'll find during volcanic eruptions you'll find large amounts of water that are either collected or incident or nearby volcanic activity suddenly released, and in training, lots of solid material that basically makes a giant, thick, viscous flow of solid material. This is a general view of those four types of mass wasting, of rapid mass wasting events: slumps, rock slides, debris flow, which are often confined to channels, and earth flow, which we saw up here at the bottom of the slump. But an earth flow is a rapid but less steep and less curved movement of earth that doesn't occur in blocks. This refers to the previous slide. It's out of order. Apologies for that. But earth flows are controlled by what's called liquefaction. That is, when water saturates soil, soil can actually behave, or solid material can behave with liquid properties. That is, it behaves in a cohesive and non-consolidated manner. It's a real-world picture of an earth flow, relatively small scale. Let's get back to where we were. I'm clearly not a master of the PowerPoint, but hopefully I'll get better as the course goes along. Slower forms of mass wasting are creep and solifluction. Creep is just what it says, the movement of soil and regolith, which is, again, loosely consolidated geologic mineral material. Creep is something that occurs over days to months to years, or decades even. Solifluction is characteristic of the higher latitudes, where permafrost, that is frozen soil layers at depth, typically in cold climates or higher latitudes. That is, if you look at the globe, you'll notice that the latitudes go from 0 at the equator to 90 at the poles. And when we talk about high latitudes, we're talking about getting closer to the North Pole or closer to the South Pole, where those latitude numbers are going up. Creep occurs during expansion and contraction of soil layers due to freezing and thawing. Movement of surface layers can go up and down, up and down, up and down. As we talked about, how ice when liquid water freezes, it actually expands. If the surface during warmer temperatures is here, when you expand during frozen times, all that liquid water that's in the soil expands and causes that soil surface to go up. When it thaws and comes back down, it moves down slope. The next year, or the next cycle of freezing events, when that soil layer here expands upward, thaws, creeps back down. And so what you get is a slow, either annual or subannual movement of the surface layer downslope. And you can see it's dragging these bedrock layers. This is just an illustration of if you had bedrock that was tilted up, and this is the surface of a nonconformity, which we'll talk about later in the course. You can actually see that motion in the fragments, how it's dragging those surface sections of rock, or the outermost layers of the strata down. Solifluction lobes look slightly different in that when you have a permanently frozen layer below, and you get a frozen layer that freezes and thaws, freezes and thaws, freezes and thaws, above you get kind of more of a lobular or lobe-shaped surface manifestation. Creep, you oftentimes will see tree branches or trees kind of distorted, fence posts tilted, roads kind of deformed. With solifluction, which is a version of creep, you get these lobes or lobular forms, lobe forms on the surface. And that's it for Chapter 4. I hope this was quicker than the last lecture. I think it is. And we'll move on next to Chapter 5 and Chapter 6. Thanks for your time.